I was halfway done with this video. This video that I thought was already done. But here I am redoing. I was halfway done. I realized something went wrong and I was not recording. So I'm back. Okay. So, welcome to Chem 2. You have graduated from Chem 1. And in Chem 2, we are hitting the ground running. So, this week, we are doing Experiment 11. It actually is on a topic that we covered in Chem 1, the end of Chem 1, where we were talking about heat and enthalpy and Hess's law, which you were in my class, we didn't do Hess's law. So I went over that in lecture this morning. So hopefully y'all all get it. It's not hard, trust me. So what we're doing is we're going to create a coffee cup calorimeter, and we are going to measure the temperature change for 3 different reactions. You found the enthalpy of those reactions in your pre-lab. Sorry, you did it for the net ionic equation, and I have written out here, you can see, reaction 1, 2, and 3. This is the net ionic equation. This should have been what you got for your pre-lab. Sorry, that glare is messing you all up. Okay. So the actual procedure, not difficult. You are taking a coffee cup, you're going to put it in a beaker, and then you're just going to measure the solution's initial temperature and then the temperature that you mix. When you mix 2 solutions together, you get that final temperature. So there's a few things I'll tell you about in the procedure, and then we'll strictly talk about the math. So if you look at the procedure, on the back of the first page, it says part 1. Number 3 says nest a styrofoam cup in a beaker. Those styrofoam cups fit best in a 250 ml beaker. So just make note of that. Then part 2 and part 3. In part 2, we're producing ammonia. And in the part 3, did I say part 2? Part 2, producing ammonia. Part 3, we're going to actually use ammonia. So let's conduct, for sure conduct part 2 under hood. It wouldn't hurt to do part 3 under hood as well. Might not hurt to do all 3 of them. But for sure 2 and 3, okay? Okay, so then we get to our data sheet. The only thing that you're actually getting in lab are your change in temperatures. That's it. And it's not hard. I think where you're going to struggle the most is the data analysis. And I was looking at old videos, and it really looked better when my notes were done. So I'm really sorry. They would have been done had I known I was going to have to do this video, because y'all know I talk with my hands. Okay, so let's look at the data sheet. Number 1 says calculate the amount of heat energy, which is Q, produced in each reaction. Use 1.03 gram per milliliter for the density of all solutions. You're going to use the specific heat of water, which is 4.18 joule per gram times degrees Celsius for all solutions. So reaction 1, 2, and 3, essentially they're going to be the same thing. The only thing you're ever changing is your delta T. And you're using the delta T from above in the table. So Q is M times specific heat times delta T. All right, well, we don't know the mass of these solutions. We know that we used 50 mils of one reactant and 50 mils of the other. So together that makes 100 mils. Well, you're given that density so that you can convert it to a mass. So if I use 100 mils, I have a density of 1.3 gram over mil. Each solution has a mass of 103 grams. Each solution also has a specific heat of water. So again, the only thing you're changing in these three, those three, are your delta T. There's your mass, plug in your specific heat, plug in delta T. Number 2, you are looking for your delta H, kilojoule per mole. If you remember from Chem 1, we did several examples like this, where your delta H is just your Q over the moles that you actually used. So how do we find that out? Well, we are given the volume and the molarity of each of these. How are we doing it like that? All right, I'm going to go with it. I don't exactly know why. So for this to get moles, we're going to say you use 50 mils of each solution. All the solutions are 2 molarity or moles over liters. So I want liters to cancel and I want to be left with moles. Well, in order to do that, I've got to convert this to liters. Do that. I just move my decimal. Replace this to the left. Convert 50 mils to 0.05 liters. So that gives me 0.1 moles. I feel like you can't really see. Okay. So here we use the total volume. Here we're just using the volume per reagent. I'm not sure if, never mind, just do it like this. Don't mind me, okay? So for each of these, you're going to take your Q that you found in part 1 and then divide it by 0.1 moles. That 0.1 moles doesn't change because every reagent we used 50 mils and a molarity of 2, so that doesn't change, okay? Number 3 is kind of confusing. It says use your answer from number 2 and Hess's law to determine the experimental molar enthalpy for reaction 3. Let me show you. All right, so over this board, I'm sorry about that glare. I have 3 equations written. I have the first equation. Then I have the second equation, but I have reversed it. When I reverse it, according to Hess's law, I change the sign on my delta H. And when I do that, you'll see several things cancel, my water and my hydroxide ions. So if I bring down everything that's left, this is exactly reaction 3 that you wrote out in your pre-lab. which corresponds to reaction 3 that you did in lab. So what you're going to do is you're going to take your reaction 1, so what you got for reaction 1 in part 2, plus the reverse, so you change the sign of your delta H from reaction 2. That's going to give you the delta H of reaction 3 using Hess's law, okay? Yes, you already have a delta H of reaction 3 that you calculated in part 2, but now we're trying to determine if Hess's law is accurate or more so our lab skills accurate. Okay, so for number 3, I'm going to take my delta H from reaction 1, then I'm going to add my delta H from reaction 2 that I have changed the sign on. Okay, so if it's positive, it becomes negative. I don't want to drill that in, but I think y'all understand that. Okay, then number 4 says use Hess's law and the accepted value of delta H from your pre-lab. So what you calculated in pre-lab on reaction 3, how do the accepted values compare to your experimental values? Okay, are they close? Are they way off? One positive, one negative? Tell me. Does this experiment support Hess's law? If it does, great. If it doesn't, suggest ways of improving your results. Okay, so I think I've covered the math. So if you're unsure of anything, ask, we'll help you. Okay. Hope we have a great semester. Welcome back.